Hello everyone, we are going to start section 13.1, and this is going to be a discussion on sequences. Sequences are a little bit different than what we've seen in this course. There'll be a lot of notational type stuff that we will have to get used to. It is something that for those of you going into calculus will see probably in your Calc 2 course. They are very powerful, and you don't see that power until you get into either Calc 2 or Calc 3, depending on how the college has things set up. But they're powerful because we can write every function as a polynomial, an ongoing polynomial. That's where their power comes. But we're going to just get a brief introduction to some of our sequences. First of all, what a sequence is. So starting off with a definition, and we're going to say a sequence is a function. So again, a function means for everything you put in, you get only one thing coming out. And this particular function has a domain, is the set of positive integers, or some people would say the natural numbers. Okay, our counting numbers. So we'd have f of 1, f of 2, f of 3, and so forth. We'd have basically a bunch of dots if we were going to graph this. Instead of writing this notation, and it's basically it is a list of numbers in order, we kind of just list them. We like to use the letters, lowercase letters, and we like to put a little subscript on there. So our first term would be A1, our second term is A2, third term is A4, 3, A4, and then it would continue on and on forever. There's no specific reason why we used A. I could have used B's, just we will see those a little later too, but it's just a sequence of numbers, a list of numbers that correspond to the first term, the second term, the third term, and so forth. We can have formulas for these. So for example, if I had the list or the set of all of these things, and the formula that I had was 1 over n, what I can do is list them. So putting n equaling 1, that would give me 1 over 1, which is 1. So my first term would be 1. My second term would be 1 half. My third term, 1 over 3, 1 over 4, and so on. We like to use the letter n because n is kind of understood to be like a counter. You know, it counts things for us. We can graph this if we want to. We don't do a lot with the graphs. But we can graph them. So my first two, so this would be my n's if you want to. This would be my a sub n, so this would start up at 1, then 1 half, 1/3, if I can draw a third, I don't know where the third is, a fourth, and so on and so forth. So it would look something like that. Okay, let's do another sequence. So n minus 1 over n. Again, we're just going to list some terms. So if I let n be 1, we would get 0 over 1, or 0. If n is 2, I would get that 1 half. If n is 3, I'd get 2 thirds. Then I'd have 3 fourths, 4 fifths. And we hopefully can start seeing our pattern. Our pattern does lead to that formula. We'll do, I think, one more. And I like to put this guy in here. And we'll do 2 over n. Again, just listing some terms. Okay, so if n is 1, this would be -1 to the second, which is going to give me a positive number. So this would be 2. If n is 2, this is negative 1 to the third, which gives me a negative, and I'd get 2 over 2. And I'm going to leave it as 2 over 2. I could go back and reduce them. The next one would give me a positive number, and I'd have that 2 over 3. The next one would be a negative 2 over 4, positive 2 over 5, and so on. If I wanted to make sure to recognize the pattern, we could have rewritten this first one as 2 over 1. Some things to notice is that negative 1 to that n plus 1, or even if I just had an n up there, allows for this alternating sign, so the positive, negative, positive, negative. You kind of have to play with it being an n or an n plus 1, depending on where you want it to start. Remembering this is your first term, your second term, and your third term, and so on. Okay, something that shows up quite a bit in some of these sequences is something we call factorial. The notation for factorial is some sort of natural number with an exclamation point after it. The way it is defined, so this is a definition, is we start with that n value and then we multiply by all the numbers smaller than it until we get all the way down to 3 times 2 times 1, and we stop. So for example, 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. 1 factorial is just 1. We do have a special definition. We do define 0 factorial to also be 1. And the reason for that is so some of our probability pieces will actually work out. Those of you that go on further into math courses and start doing some proofs, some theoretical type proofs, this 0 factorial shows up occasionally, and you got to remember that it is 1. Another piece that kind of helps for those of you going on is to kind of think of n factorial. If I go back to my definition is n times n minus 1 and all these pieces down, I can write that as n, and then this would be n minus 1 factorial. So this again sometimes shows up nicely when you are doing theoretical proofs. You could, if you needed to, peel off 2 of the examples and then you'd have the rest. So this idea of being able to peel off pieces kind of helps. To show you where it's on your calculator, so we'll go and do this actually 6 factorial, so that if you never needed to calculate it for whatever reason. Okay, your factorial key is sometimes hidden. Mine happens to be hidden underneath the probability key. And if you look at my probability key, there's my exclamation point. And so if I wanted to use it, the first thing I would do is type in that 6. I would go get my exclamation point, and then I can hit my equals, and I get 720. That will save me time as opposed to writing and typing in 6 times 5 times 4 and so forth. Besides, I'd probably lose track as to where I was. Okay. This does grow very quickly, so it doesn't take very long for our numbers to get too large for calculators, so just kind of be aware of that. Okay. Some of the problems that you're going to see is going to be able to recognize patterns. And so when they say find the nth term, they are basically saying find a formula for this sequence. So if I look at my sequence 1/2, 2/3, 3/4, and then I just have dot, dot, dot. First of all, we're going to assume that the pattern continues, and then we have to see what that pattern is. Remembering this is our first term, so this is where our n is going to be 1, n is going to be 2, n is going to be 3. And these take time, and some people are really good at this, and some people struggle. So I try to kind of look for patterns. Like I notice at the top is exactly that n value. So my numerator I can write as just n. The next thing I notice is my bottom is one more. So if I want one more than n, that would be n plus 1. So my nth term, if I wanted to write a sub n, is this n over n plus 1. Let's try another one. Let's do 1 over 2, 3 over 4, 5 over 8, 7 over 16, and so on. All right, again, this is n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. Now we got to think. So we want a formula. Okay, this is kind of going up by 2's every single time, or my odd numbers. So let's see. Kind of relate it to my, because it has to work for all of them. If I think about it, maybe I'll do the bottom first. Maybe that's easier to see. I don't know. I see 4. I see 8. I see 16. And some people would say, well, that's just multiplying the next one by 2, which it is. So think of this as 2 to the first, 2 to the second, 2 to the third, or we get that 2 to the nth power on the bottom. The top, the way I want you to kind of odd numbers, if you look at it, if I take this 2 and multiply it by 2, subtract 1. Take the 3, multiply it by 2, subtract 1. Take the 4, multiply it by 2, subtract 1. So I can write my top as 2n minus 1. In fact, any odd number, so if you see odd numbers, they'll either be in the form 2n minus 1, depending on where you start, or 2n plus 1, or you can add or subtract an odd number here to get your starting point. Even numbers, so if you go like 2, 4, 6, they'll take on that pattern 2n. So 2, 4, 6, and so forth. So kind of look for those things too, those odds and evens, which kind of spoiled the next one for me, but that's okay. Okay, so we have a negative 2, 4, negative 6, 8, negative 10. If you notice, these are our even numbers. So we do get that 2n that I just mentioned. Oops. However, we also have a negative, then a positive, then a negative, then a positive, which means we're going to have that negative 1 in there to a power. Now we want the first one to be negative, that second one to be positive. So I'm going to just put n here and see if it works. So if n is 1, I do get a negative. N is 2, I do get the positive. If you want to do that alternating idea, you will either use a negative 1 to the n, or most people will do a negative 1 to the n plus 1, depending on where you want it to start. If you want it to start being negative, you'll use this one. If you want it to start being positive, you will use that one. Because this would say if n is 1, I start with the 2 as my exponent, then 3, then 4, and so forth. Okay, this is just a brief introduction to these sequences. We're going to continue this discussion in the next video.